Okay. Let's see if it's working. All right. Okay, so this week we're going to go over mainly Thevenin and Norton equivalent circuits and then op amps. I know you guys also learned about BJTs this week, but I believe those are not going to be on your quiz. You might have mentioned that in class, but judging from previous quizzes, I think it won't be. I'll go over like one question. I'll like do the homework question that you had on BJTs just as a refresher, but I believe this quiz should mainly be on Thevenin Norton equivalents, maximum power transfer, and op amps, both either simplified op amp or like the model that you learned. So this is what review session 3, 4. I think this is 4. And today is 9/26. All right. So to get started, we got Thevenin. I'll start with Thevenin equivalent. Circuits. So the idea with Thevenin equivalent circuits is if you have some complicated circuit, I'm just gonna draw some symbols on here and not give any of them values. Let's say over here we have a dependent current source or something, and then I don't know, another resistor. Down here we have another current source, yada yada. It's very complicated. But then we have these terminals A and B, and we want to say, okay, if I don't actually care about circuit, I just want to know how it would be, how these terminals A and B would be affected. And then what we're going to do is, through a couple operations, we're going to simplify it to a circuit that looks like this. And this circuit will have exactly the same behavior as the circuit on the left, but it'll just be much simpler and much more straightforward. Similarly, Norton equivalent circuits is the exact same thing, just when you source transfer this circuit you have here. So instead of being a voltage source in series with a resistor, it becomes a current source in series with a resistor. So this is Thevenin. This is, and this would still be RTH. And this would, or it might be IR. I'll say RN for Norton. So that equals RTH. I n equal to VTH over RTH. So I'll do some I'll do some examples of that later. And then moving on, the next thing you learned is maximum power transfer. So the idea there is, if I have, this goes back to the Thevenin Norton, or the Thevenin equivalence. If I have a circuit like this, and I have some resistor, so let's say to the left of here is my power supply, and it has some voltage it's supplying and some internal resistance. Then we want to figure out what's the maximum power that can be transferred to this resistor. What that's going to be, or what the maximum power, yeah. So we want to figure out what resistance will, both what resistance will transfer maximum power and what that maximum power is. So the resistance, the maximum power is found when the resistance of the load equals the internal resistance. You can do some math to figure that out, but that's just what it's going to end up being. It's basically, as you increase the resistance, the current's going to go down, and that'll reduce the power. But if you decrease the resistance, then less power gets dissipated because the resistor has lower resistance. But you end up finding that the maximum is when RL equals that internal resistance. So what that also tells you is, back up with this other circuit, if you were to put a resistor here, and you wanted to find out what the maximum power that can be transferred to that resistor is, it would be very good to turn it into this Thevenin equivalent, and then you'd say that the resistor should be equal to RTH, and with this formula I'm about to give you, you can determine what that maximum power transfer will be. So that maximum power transfer will be P max equals, it is VTH squared over 4 RL, which, as I said earlier, is VTH squared over 4 RTH, or Rn, depending on how you're looking at it. Okay, I'll do a maximum power transfer problem for you guys in a bit. Then op amps. So an op amp is a circuit element that looks something like this, where you have VCC minus VCC, V out, and then like VA and VB, or I'll call them VP and VN, which is your plus and minus. And so the model that you guys have learned in class is something like this, where you have your, let's pretend I did this the other way, because this matches the picture that I have put up here. It's going to be we have our VN and VP, and then to that we have our R internal, or we can call RI. This would be our VN. And then we have VCC and V minus CC aren't that relevant right now, but they are actually quite relevant. And then for the output, I'll actually just not draw the VN or the VCCs right now. And then what we have is we have some like imaginary ground that has the value times VP minus VN. And then some internal resistance to the V out. And we can call this R out. And so what this is saying is that the output of your op amp, it is the amplified difference of VP minus VN. So the reason it's called an operational amplifier is because you can use it to perform operations, namely addition and subtraction of two voltages. What we find though is that in real op amps that you'll use, Ri is usually very high, so we can end up approximating it as infinity, and R out goes to like 0. And then what that also says is that that current going into VP or out of VP and into VN and out of VN, which I'll call like IPN, is going to be 0 because we have an infinite resistance on that resistor. And then the other thing is that A is going to be very high for actual op amps, and we can kind of just say that that also goes to infinity. So what we end up getting then is this kind of model. So this is the real, and over here we can have the ideal op amp. I believe on this quiz you may or may not have a question on real op amps, but that should really be the only time you ever have to deal with that. With the ideal op amp, we have, yeah, like I said up there, I equals 0. In most of the circuits you're going to see in this class, what you'll end up having is that we have some kind of feedback loop from V out to Vn or V out to Vp. And what that ends up happening is that you'll have Vn equals Vp due to some feedback mechanism. We'll get to that in an example problem. I'll just show you how it works. I'll put a little star on here to say that it's for the blue. And basically V out is basically going to be determined by your calculations assuming these two factors. And then the other thing that's important, they might have a quiz question on this. We have that V out is always going to be less than VCC, or less than or equal to VCC, and greater than or equal to negative VCC. So if you end up doing a question and you get that, let's say on the top we have like a plus 15 volts. On the bottom, you have a minus 15 volts. And then your V out, let's say you do this, you do some kind of circuit. I'll just like draw a little example one right now. I'll get back to it in a moment though. We have this. We have a voltage source. And we get a V out, and we find that for this kind of circuit, I'll show you an example of this actually. So here the V out is going to end up being minus R2 over R1 times V in. But if we end up getting that V in is, let's say if our V in is like 6 volts, and let's say this had a gain of 3, and you get that your V out is 16 volts, then what you'll find is it actually clips down to 15 volts. What you learned in class is that this can be represented as this kind of a transfer characteristic where we have a V in and we have a V out. So for this, I'll go back to this model. Let me copy this. This will all make more sense when I do some example problems in like 10 minutes. Let me finish. Okay, there we go. So if we define V plus minus Vn as V in, then what we'll end up seeing minus VCC, and I'll say VCC minus VCC. I would say that's not quite right. It would be like VCC over A and negative VCC over A. What we end up seeing is that these end up matching up until you get to this point, and then it'll be clipped at VCC. So what that means is that your V out cannot go above your VCC, when it cannot go below your minus VCC. So you're going to get that kind of thing. The idea there is that this is like a real thing. It cannot create a voltage higher than its input. And so this circuit, the op amp is like its own circuit that you're going to use one in the lab in a week or two. It's its own little package, and it has these 2 voltage inputs, and it cannot output an input, or it cannot output something bigger than these 2 currents or these 2 voltages you're giving it. Okay, then last but not least, I'll go over the BJT model that you learned in class really quick. So the BJT is something that looks a little bit like this, where you have your base, you have your collector, and you have your emitter. Those are the 3 names of the thing. And the model you learned for that in class is, for any question you're going to get with it in this class, you're going to end up getting this model. There's other models for it, but you'll learn that in other classes if you're an electrical engineering major. Otherwise, it won't really affect you. And I'll just put a little circle here so it's clear. You end up finding is that this is a pretty good approximation for a BJT. My face. Yeah. And what we find is that we have this beta factor, which is often called the current gain. So what we see here is that IC equals beta times IB, or we'll capitalize that to match the notation there. And from that, through Kirchhoff's current law, because they both go down like here, you can say that IE equals beta plus 1 times IB. Okay. Yeah, and I'll do one practice problem with that later. Judging from past year's quizzes, I really don't think you'll have a question on BJTs. If he mentioned it in class, I think when I took this class, he mentioned in class that they're not going to be on the quiz. So if that's the case, let me know. But at the moment, I'm just planning on going over that one question you had on the homework. And with that, I will get to some problems. So to start, I will do this question that was on, this question is about maximum power transfer. So this will involve both Thevenin equivalence and then maximum power transfer. So this could be something like a quiz question. It might be shorter than this, just because this question is a bit long. But this will be maximum power transfer to our load. Give me a second to draw the circuit. It's going to be, we've got a 30 volt source here, going to a 5 ohm resistor. We got a 3 ohm resistor. We got a 2 amp current source. We got a 6 ohm resistor. And then we got our load resistor. Lowercase a. And this is our load. And yeah, so this question is asking for what is the maximum power that can be dissipated through our load. Remember, power is current times voltage. So we want to find out what the biggest power we can get is out of this R load. And so for that, you both need to figure out what is the value of R load and then how much power will that produce. So the way we learned how to do that is we're going to turn this into the Thevenin equivalent. And then R load will equal your R Thevenin, and the power max is going to be your VTH squared over 4 RTH. So let's get started. So the way that you find the Thevenin equivalent with respect to points A and B is what we're going to do is we're going to redraw this circuit just a little bit here. And we're going to pretend that this load resistor isn't here because we want to figure out how this circuit would act just if the load resistor wasn't there. So to do this, you can do it really any way you want. You could either do mesh current or node voltage. You're just trying to figure out the voltage between A and B. So the way I look at this, I see, okay, we have a current source here. That gives me a lot of information. What I'm going to do is I'm going to say we're doing 2 mesh currents. So we're doing a mesh current method. We have I1 and we have I2. And then we don't need one for here because this is an open circuit here, so there's no current there. So real quick, we see we have I2 is going to equal that -2 amps just from this source, because I2, I always define them as going, actually I'm not very consistent. Here I define them as going clockwise, and since this is going down, we're going to say that I2 is -2 amps. And then for I1, we get an equation that's like 30, or not, I1 equals, we get 0 equals -30 volts plus 5 I1 plus 3 I1 minus I2, which we can simplify a bit more because we know I2. 3, and then that's going to be I1 plus 2. Oh, and the reason we're doing all of this is because since there's no current going through here, that means the voltage difference across this is 0 volts. And then that means that this and this are still A and B. And since there's no resistor on the top and no resistor on the bottom, that means if we can find the voltage across this resistor, then that's going to be the same as the voltage across these terminals over here. I just swiped a page by accident. So what I'm doing is I'm finding I1 and I2, because then you can just multiply those, or we can find the total current going through this resistor, and then we can find the voltage across that resistor, and then we can find VAB. So I'll just continue doing that. This is now just going to be algebra. 30 equals 5I1 plus 3I1 plus 15 or plus 10 Subtract 10 from both sides, combine terms, you get 20 equals 8 I1. Let me make sure I'm doing this right. I think I'm doing this right. I'll check once I get the final number. So that I1 equals 20 over 8 or 10 over 4 or 5 over 2, right? I think I can simplify it that much. 5 over 2 amps. So then we have 5 over 2 going, or we want to find the voltage between A and B. So I'm going to say that A is positive, B is negative. This will be our VTH. So that means if I want going from top to bottom to be positive voltage, then I'm going to say that I1 is positive, because if I1 is positive and I2 is negative, then that's going to match what we want. So I1, so that means the current through that resistor, through that 3 ohm, is equal to that 5 halves, equals 2.5. It's equal to 2.5, or I'll fully write it out, is equal to that I1 minus I2, which equals 2.5 minus negative 2, because that makes sense. Because if you look at this, there's nowhere for it to flow to the right, so it ends up flowing to the left and then probably down through here. So this ends up being equals 4.5 amps. So then if we have 4.5 amps, then we can find that VTH equals the voltage of that 3 ohm resistor, which is going to be 3 ohms times that 4.5 amps, which gets us, what is that? It's like 12 plus 1.5, 13.5 volts. And let me make sure. Oh, I did a little mistake somewhere. Hold up. Get three times. Oh, I'm silly. I said 3 times 2 is 10. 6. Oopsies. Oh, why is the power of v squared over 4r? I'll get to that. I'll explain that in a sec. You can either take it as a formula or I'll show you a little proof of it. Okay, wait. So let me just change this a bit. This becomes 24, and then instead of 5 halves, you'll get 24 over 8, which is 3 amps, which is 3 amps. Oopsies. And then we actually get 3, and that's going to be 5. And this is going to be a different number. This is going to be a different number. Yeah. So make sure you watch for little mistakes like this. If you do a little mistake like that, hopefully whoever's grading it will find that and not take off as many points. But it's always better to get the question right, you know? It makes grading easiest. It makes your grade the best. It makes everyone happy. So we get 15 volts as our V equals VAB equals our VTH. So we have our Thevenin voltage. But that's only half of the picture. We need to also find the resistance. So there's 2 ways to do that. I'll go through both ways just because, or I'll do one way right now, and then for another question later, I'll do the other way. Just because there's an easy way and there's a more complicated way, but sometimes you have to use the complicated way. I will start for now with the easy way, though. I'll go to the next page. So finding RTH, the way we're going to do that is, this is only here because so the way we're going to find RTH is you basically just pretend this circuit has no sources. So we're going to deactivate all of the constant sources. The reason I said earlier that you cannot do this for some circuits is because if it has a dependent source, then you cannot do this method. So as you hopefully just saw there, I took the voltage source and turned it into a short, and I took the current source and turned it into an open. The reason for that, if you think about like what's the opposite of those two sources, so a voltage source has a difference between its terminals, whereas a wire has 0 voltage between its terminals. So you can think of a wire as like a 0 volt source. And then similarly, a current source has a current along that path. If you have an open circuit, then you have 0 current along that path. So yeah. Anyway, so once we're here, we've neutralized the sources. Then what we do is we just like simplify these resistors until we get one resistance between here and here. So to do that, I'll redraw the circuit real quick to make this make a bit more sense for you guys. Oh, I just realized I forgot to label this. I guess it didn't really matter in this question anyway, because there was no current through it. But for this part, it'll matter. So this is a 6 ohm. Anyway, so this circuit is the same thing. If we just kind of move the resistors around a little bit, you'll see all the connections are going to stay the same, but it'll look a bit more like something that will make sense to your brains, I hope. So here we have our 6 ohm, and we have our 5 ohm, our 3 ohm. So here, hopefully you all know how to simplify this. You're going to take these two in parallel and then add them to this 6 ohm. So these two in parallel is going to be 5 times 3 over 5 plus 3, which gets us 15 over 8. And then you can imagine that that'll turn into something like this. And then you will add these two together. And then if I were writing this down, I don't know, I'd just do it kind of stupidly like this. So 15 over 8 plus 6 is, I'm just going to plug that into a calculator real quick because I cannot be bothered to do that in my head. 1.875 plus 6 is 7.875. So we get our RTH. And so, yeah, what we end up getting there is, I'll draw out the final circuit just to be clear. Equals 7.875. We end up getting is just a single, I'll write it out to the side. Get a single resistor between the two with a value of 7.875 after you neutralize the sources and combine all the resistors. So what that tells us is that this is our RTH. And then a final step for the question, you have to do this or else you won't get full points, is you draw your final Thevenin. Oh, there's still another step because we have to find the power. But if this was just a Thevenin equivalent circuit question, you would have to draw this final circuit where you have your VTH, which we found to be 15 volts, and our RTH, which we found to be 7.875 volts, or not volts, ohms. And this would be our Thevenin equivalent circuit. It's a B, handwriting. Yeah, if you were asked to find a Norton equivalent circuit, you could do the exact same thing. This is just for sake of example. This was not asked on this particular question. But what you do is you'd say, okay, we have a current source. As I said earlier, this is just a normal source transform. So this will have a value of VTH over RTH, which is, I really don't want to write that. It's just like some basic division. It would be that. It would still have the same resistance. That's how source transforms go. And then this would be VTH over RTH. But that's not really asked in this question, so I'll erase that. What is asked, however, is what the original question, we had this load resistor, and we want to find what is the maximum, what is the value of, and what is the maximum power of this load resistor. So I'm just going to say it can be shown, I think Zorman likes saying that. So it can be shown that the biggest power will be dissipated through a load resistor if it has the same value as that Thevenin equivalent. If you want to do the math on that on your own, like, go ahead, but it's not that important. If you think about it, the bigger resistor, I said this earlier, but the bigger resistor is going to make less current flow through, which will dissipate less power, and a smaller resistor will dissipate less power because it's like less resistance dissipating less heat. And there's a balance somewhere when you have that second resistor in there, and you find that that balance is when R load equals your RTH, which is going to be 7.875 ohms. And then that formula I showed earlier is P max equals VTH squared over 4 RL or RTH, depending on what you want to say, which here is 15 squared over 4 times 7.875, which if you plug into a calculator is about 7.14 watts. Real quick, I'll show this formula's derivation. It should be pretty straightforward. It's just, if you generalize the circuit, This is, I'll just call this V. This can be R, and then this will be the same R, again, for the reasons I listed earlier. If we want to find the power dissipated by this R specifically, then first we have to find the current and the voltage through it. So the current is going to be V equals IR, just general Ohm's law, then I equals V over R. In this case, this is the general case, or this is just Ohm's law, but then I'll give them names. They can all be R1. I'll call them RTH. Okay, so then we see that I'll call this I, equals, it's going to equal your VTH over 2 RTH, because you have these two resistors in series. And then the voltage across this RTH on its own, by like a normal voltage division, is just going to be 1/2 of VTH, because you have two resistors of the same value. They're both going to have the same voltage drop across them, so it's going to be 1/2 RTH, or 1/2 VTH. And then P equals IV equals that VTH over 2 RTH times 1/2 times VTH. And that gets you that formula that I showed you earlier. So if you want to go through this, if you don't want to remember the formula, that's very fair. This is just a pretty straightforward, like, you can find the power through that resistor if you just go through your basic circuit theory. Yeah. So that's that question, and this would be your final answer. Okay, I still got some time. I also started a bit late, so I'll give you guys the benefit of the doubt on that one. I'll do a op-amp problem real quick now, I think. Yeah. So I'll do an ideal op-amp problem, just because that's probably what'll be on your quiz, because you don't have that much time on your quizzes. So we got resistor, we got another resistor, this little branch here, ground, and up here we see the out. These resistors all have values. These are in kilo ohms, which is just 1,000 ohms. Most systems that you'd work with in real life, or most circuits you'd work with in real life, are going to be in kilo ohms, just because you don't need that much current for most things. And yeah, so then we're going to have 9 volts and negative 9 volts as our DCCs. And this is asking you to just determine V out. So to do that, how I'd always start these is you want to figure out, so let's review what we know. So we know that Vn is going to equal Vp, and there is no current going in or out of these. In equals Ip equals 0. If you write those two things on your quiz, you'd probably get some points for that. So to start this, if you look here, we don't know anything about VO yet, so we can't really say anything about Vn. However, Vp has everything here defined, and we can figure that one out. So this is Vn, this is Vp. So if we just write a single node voltage equation for Vp, we can say that 0 equals Vp minus 1.2 volts. I'm just going to say that both of these currents are going out, and then this one's 0, so this one doesn't matter. So the one going down, we have Vp minus 1.2 over 64K plus Vp minus 0.5 over 80K. If we just do some math. You multiply both of these by like, what's a common factor here? 8K or 16K? Yeah, 16K. If you multiply both of these by 16K, you'll get, no, that's not enough. Multiply both of these by like, what are they doing this? I don't know. However you want to do the algebra. I'll just or 8 plus VP minus 0.5 over 10. And then I don't know, move one to the other side. You get it's really just this is really just algebra. I'm just doing it in a stupid way. I'm just gonna kind of do it all at once here. You move that to the other side, and then you're gonna have VP times 1/8 plus 1/10, and then you divide that over, and you end up getting that VP equals 0.89 volts. You can do that in a calculator. Hopefully, you know enough algebra that you don't mind about that. What about the second method for? Okay, why is RT? Okay, let me address these questions real quick. RTH is our load. It's just that I don't want to go through the derivation of that because it's a bit more complicated. But yeah, for that's in general. So for any question where it asks you to find the maximum power through a resistor, what you're going to have is you're going to have some kind of thing. You have a voltage source, and that voltage source has some kind of either internal resistance, or this is a Thevenin circuit and has a Thevenin resistance. But you have this voltage source in series with a resistor, and then you have some load resistor. That load resistor is always going to be equal to this one. That's just the configuration that will get you the maximum power out of this resistor. Yeah. And then the second method for the last question, we need to add a 1 amp or 1 volt to the circuit. So the other two methods he taught are the short circuit current method and the test voltage method. I don't really like the test voltage method. I don't really see any use to it. So the other method, I'll do that now because I've moved on to this. But okay, I'll just move this down here for a sec. So the other method was, sorry to get sidetracked, but I just want to make sure I'm getting to the questions that I see. So the other method is, instead of having this load resistor here, you would replace it with a short circuit, and then you want to find this ISC. So here, this would be, I don't know, I'll do a I1, I2, I3, and you do this mesh current. You can see here that this ISC is equal to I3, just because it's going around here, it goes through there. And when you find that ISC, so you still find the Thevenin voltage in the exact same way. So we found our Thevenin voltage, and then what you find at the end of this is you have an ISC and a VTH, and you know V equals IR, so then R equals V over I, so then our RTH is your VTH over your ISC. Here, after you do all this math, you're going to end up getting whatever 15 divided by 7.875 is. If I have time, I'll show that as an example, but for now, I'll just leave you with that. You have to do this method if your circuit has a dependent source somewhere. So this circuit was like 2 amps times, I don't know, VX, and this was VX or something. Then you cannot do the method where you just remove the sources, because you can't do that. You can't neutralize a dependent source like that. It's just not something you're allowed to do. So I will, I don't know, I'll just move that up there a little bit. Okay, I'll leave that there. Back to the op amp. So here we found VP, and then we say that is also equal to Vn. And once you have that, you're almost done. So the one key thing about op amps that you can't forget is that this is unknown. We cannot use this current, which means we can never write a node equation for V0 because we don't know what is coming in or out of the output of the op amp. But what we can do is we can do a node analysis for Vn because we can use V out as a variable. And we know that there's no current going to the right. That's just going to be 0. And then we know that this down here is like 0 volts, so on and so forth. So we can say that this is another node equation for Vn. We can say, just for the sake of making the math a bit easier, I always say that every current is going out. So we can say Vn minus 18K, minus 0 volts over that 18K plus Vn minus V out. So this is, the first one is this leftward path. The second one is that upward path. Sorry. And that's over 72K. And again, you do this pretty similar way. I'm just gonna kind of do it all pretty fast again. So the most straightforward way to do this is you just leave everything in fraction form. So we're gonna have Vn 1 over 18K plus 1 over 72K. That's just gonna be from this and this. And then it's gonna be minus V0 times 1 over 72K. And then you move that V out to the other side. And we know what Vn is. So we have V out times 1 over 72K equals, what's Vn? It equals to Vp, which is 0.89 times that 1 over 18K plus 1 over 72K. And then that means that V out is equal to this whole expression. It would have been faster. Oh God, yeah, it would have just been faster to write it down again. 0.89 times 1 over 18K plus 1 over 72K times 72K. And then that, you can just plug that into a calculator. You're going to end up getting that V out is 4.45 volts. A more complete way to do this is you also say that this like plus IN, but then IN is 0, so you just ignore it. I think that's what Zorman usually does in example problems in class, but you can really skip that step. It's not that important. So that's kind of a basic op amp question. I'll do like one more. This is like a common one that you might see. This is the circuit for an inverting amplifier, which is like one of the, I think you make it in lab in a week or two, or maybe this week, I'm not sure. But this is like the most basic amplifier you can make with an op amp. It's based on the rules you know. Pretend that's there. This is R2, this is R1. So what this tells you is that, so that means V plus equals V minus, or Vp equals Vn equals 0 volts. And then with just a normal node voltage equation, you say, okay, we have a current going that way, we have a current going that way, and we have a current going that way, but that one's 0, so you ignore it. So you'd say Vn minus Vin over R1 plus Vn minus V out over R2. And then Vn is 0, Vn is 0. So we end up with 0 equals negative Vin over R1 minus V out over R2. We want to figure out what R2 is in terms of Vn. You'd subtract it over to the other side. V out over R2 equals Vn over R1, and V out equals negative R2 over R1 times Vn. And that's another example. Like that, honestly, it's probably not going to be something that easy on a quiz, but the general flow is you figure out either Vp or Vn. You use that to figure out the other one because they're equal to each other. And then from there, you write a node equation based on one of those two. Yeah, I have time to do like one or two more questions. Let me see. I don't really want to do a BJT question because I'm like pretty certain that won't be on the quiz. I'll do one question with the op amp SAD, the bad one. The one with the real op amp. Where is that? Yeah, okay, this one's pretty straightforward. So we have this op amp. This is something you might actually have in the quiz because this is like pretty doable in your time frame. We have this. I messed this up drawing up. We have this circuit. K, 4K, 7K. That's it. So what this is, and then we have that R out. If you remember from this model I showed at the beginning, oopsies, I didn't mean to make that page, but this is the model we're working with here. We turn this op amp into this. So R out is the one going out of it, and then we have that Ri, and we have that A as our gain. So this question, it's given that Ri equals 500K, a big number. R out equals 5K, which is a relatively small number. And A, or our gain, is 300,000. So this question is saying, apply the real op amp circuit model and then use node voltage and write down all the equations you might need to solve this question. So if we want to redraw this using the op amp model, what we'll do is I'll copy this over from the previous page, both for myself doing this problem and so that it makes a bit more sense. Copy. So we have this. And so the key thing you want to remember here is that all of these grounds are like connected to each other. It's a common point. They just do that to make it a bit easier to draw the circuit. So here, what we end up getting is a very long bottom part. And here we have our VP and our VN, and they're connected to each other by that 500 kilo ohm resistor. And then this VN goes over here to that. This goes up here, maybe like there or something. And then this is connected to V out. And if we remember from this, V out is going to be, I'll actually draw this over a bit more to the right so we have some more space. Our V out is a dependent voltage source connected to another, this is our R out, so this is going to be a 5K. And it's going to be like that. And this would be our V out. So it's telling you to write the node voltage equations that you need to solve for V out. And this, of course, is going to be 3000, which is our A times VP minus VN. And then I'll write everything else. It'll take a while. You guys learned a lot of stuff this week, so I'm sorry if I can't quite go over all of it. With the BJT question, if you're curious, just look at the example in the homework. The answer key is done quite well. So here I'll redraw this circuit just a bit more simply to make a bit more sense. I'm not going to fill in the values here because that'll take a while. Actually, yeah, so we have yeah. And hopefully you guys can see how this is the same circuit. The connections are all still the same, and then this would be our V out. And then this is like our ground down here. So if we're doing a node voltage, then what we want to do is we want to pick, okay, what are our nodes that we care about? And, what are the important equations? So the nodes that we don't exactly know, the main one is this. And then Vn and Vp from earlier are going to be here and here. And we need those because this is still A times Vn minus, or Vp minus Vn. This is our Vn. This is our Vp. So this can be Vx, I guess. Or did I do that right? Oh, my fault. Okay, right. They added new AI update to GoodNotes for some reason. Kind of weird. But this is Vn, because if you look at the diagram, this is Vn, and that's directly connected to this top part. So this is your circuit. You have Vn, you have Vp, you have Vo, and we want to find all the equations you need to write to find Vo. So let's start with Vn. And it said use node voltage equations. So for Vn, you would have that 0 equals Vn minus the Vp over 500K. You'd have Vn minus V out over, that was 7K, I think. Did I get that wrong? Oh, yeah, over 7K. Plus, again, I always like to assume that every current is going out, just it makes your numbers a lot easier. Plus Vn minus that 7 over 4K. And then plus, what am I missing? I'm missing this one, and this is 6 volt, and this is a 3K. Plus Vn minus 6 over 3K. So that would be one equation. And then we still have two more unknowns. We have Vp. Vp, though, we can easily see is just 4 volts. So that defines Vp for this equation. And then we'll need an equation to define V out. So V out, we can do a node voltage on that equation. So this is our 7K, this is our 5K. So we're going to have V out minus that 500,000 times Vp minus Vn over 5K plus that V out minus Vn over 7K. And these three equations would be your final answer for this question. This is the most you're going to have to do on a quiz. I know that took a while, but really all it was just applying this op-amp model. The op-amp is the stuff in this circle. Yeah, the stuff in this circle. That's kind of, if you do it really nicely on a quiz, you can sometimes like draw the triangle to perfectly match, like if you do it like that. But you apply the op-amp model, you redraw the circuit so that it makes more sense to you. and then you'd write the equations just as if it was any circuit you found on any question. And yeah, so hopefully that's good enough. I'm assuming on your quiz tomorrow, you're going to have one question about Thevenin equivalence and one question about op amps. So yeah, based on everything, one step I missed at the end of this is so this was the op amp question I did earlier where we're using the ideal op amp model. So we got this number, but we didn't check to make sure that it's within this plus and minus 9 volts. However, it is, so you don't have to change it. But you always have to make sure that your output VO is going to be within this range, because he might try to trick you on a question where you'll get everything right, but then the output final voltage will be like 15 volts, and you only have plus or minus 9 on your input, so you can't have a plus or minus 15 volts on your output. So what would happen then is, let's say this was hypothetically 15 volts after you do all of your math, yada yada, but your input's only plus or minus 9, so that would end up being, it tries to go to 15 volts, but it can't, so your final would end up being 9 volts because it gets clipped to that 9 volts, which is the kind of thing you saw here, where it like tracks pretty well. And you'll end up doing a lab where you do the same thing. This will all make more sense in like 2 weeks when you've done the lab. It's kind of annoying that they do it in this order, but what can you do? But you'll end up seeing, yeah, the op amp gets you this kind of graph for V in, V out. Yeah, is there anything else you guys would like me to go over? We're pretty much out of time, but I could, I don't know, answer a question or something like that. I'll wait for like 10 seconds in case anyone wants to type anything. Okay, in that case, that's about it. If you have any other things you want to go over, I would really look over the homework answers. They're written out very nicely in very orderly steps. You can rewatch this. I'll upload this as a video. You can rewatch it if you want to see me do some of these questions again. Yeah, good luck on your quiz tomorrow. I wish you guys the best. And that's all for now.